And number 45 from section 4.6 is an example having to do with revenue. So we have a baseball team playing in a stadium that holds 55,000 spectators. And if they charge $10 a ticket, attendance has been on average 27,000 people. If they charge only $8 a ticket, they'll increase their attendance to 33,000 people, so they'll increase it by 6,000 people. And so part A is asking us to find the demand function, assuming that it's linear. So demand, we can do either price as a function of attendance or attendance as a function of price. But looking ahead to part B, how should ticket prices be set? I think it makes sense to let P be my input variable, and that can be ticket price in dollars. And then I can let A be attendance. And just to make things again a little simpler, I'm going to make attendance in thousands. So I'm going to set up a little table for myself that when the ticket price was $10, attendance was 27,000. And when they lowered the ticket price to $8, the attendance went up to 33,000. And so right away I can see my slope, that my attendance went up by 6 when the price went down by 2. And so that's going to create a slope of -3. But, right, and again, just keep in mind that assuming demand is linear, sometimes we use actually quadratic or exponential functions for demand, but we sometimes use linear as well. So for slope, I can do change in attendance over change in price, and that gets me, again, -3. Now, in terms of coming up with an equation for demand or a function for demand, I can sort of follow this table down until I get to a price of 0, or I can say, okay, I have attendance equals some slope times price plus a vertical intercept, and when my attendance is 27, I have a slope of -3 times a ticket price of $10, and that would give me 57 as my vertical intercept. So the demand function as they say, assuming it's linear, would be A, attendance as a function of price. That would be -3p plus 57, or you could write it 57 minus 3p. Either one will work just fine. Now, we should note that the ticket price obviously has to be positive, right? Attendance obviously has to be positive. In this case, also, attendance can't be bigger than 55,000, right? It told us that the stadium only holds 55,000 people. So actually, I guess these could be zeros. They could have nobody come to the game. And so if we worked our way backwards in this price versus attendance or in this demand function, I would get a 0 attendance if my ticket price was 67 cents, 2/3 of a dollar. And I would, whoops, I have that backwards. Sorry, hang on. I would reach my maximum of 55,000 if my price was 67 cents. Right? In other words, the more I lower my price, the more people show up. But according to this demand function, I will reach my maximum attendance of 55,000 at a ticket price of 2/3. So if you set your A value equal to 55 and solve for P, you'll get this 2/3. So if they charge 67 cents a ticket, They will fill the stadium to capacity. And then again, following in the other direction, the more I keep raising the ticket price, the less attendance I have, and I will get 0 people to attend according to this demand function if my ticket price is $19. Okay, so we're going to see why that's important in a little bit. So part B is, how should we set ticket prices to maximize revenue? So again, important to recognize what quantity it is you're maximizing or minimizing. I want to maximize revenue, so that means I need a function for revenue. Whatever quantity I want to maximize or minimize, I have to come up with a function for that quantity. Now, in general, revenue is price times quantity. That's just a basic general thing in economics. In this case, ticket price times number of people attending will be their revenue. So a function for revenue in terms of ticket price is the ticket price times the attendance, which is the demand function that we found in part A. So simplifying this a little bit, I have negative 3p squared plus 57p. So I want to find where this function is maximized, and I'm going to use my techniques from sections 4.2 and 4.3, although we might also do a little hindsight is 20/20 in a minute. Okay, but I want to find critical points. I'm going to take my r prime, which is a nice simple derivative here, and I'm going to set that equal to 0 to find critical points. In this case, my revenue function is polynomial, so I don't have to worry about places where it or any of its derivatives are undefined. And when I solve this for p, I get 57 over 6, which you may also know as 9.5. So it looks like they should charge $9.50 per ticket to maximize their revenue. But again, we have to test this out. So I'm going to set up a number line for the first derivative test. You could also use the second derivative test. Actually, why don't we do that just for a change of scene? We haven't done that yet. So in this case, the second derivative is very simple. R double prime of p is negative 6, which is always less than 0, which means my revenue function is concave down, which means my critical point is giving me a maximum, right? If my function's concave down and I have a place where the tangent line, right, so I have a concave down function, I have a place where my first derivative tangent line is horizontal, that must correspond to a maximum. All right, now again, we should go back and make sure we answer the question, how should ticket prices be set? So revenue will be maximized if the ticket price is set at $9.50. Now, in this case, we had a restricted domain, so I'm just going to make a note. In this specific example, we know that this is an absolute maximum, but in general, if we have a restricted domain, we should check, and I'm just going to demonstrate the technique. We should check the endpoints as well. In other words, we should check revenue at the low price of 2/3, and we should check revenue at this maximum price value we found of $9.50, and we should check revenue at the highest ticket price possible. So if you take that revenue function, negative 3p squared plus 57p, and you let p be 2/3, you get 36 2/3, so about $36,000 of revenue. At $9.50 ticket price, the revenue is $270.75, so $270,000 of revenue. And if the ticket price is $19, nobody comes, and so there will be no revenue, right? The quantity attendance function will be 0, so we'll have a price of $19 a person times nobody coming will give us a revenue of 0. So this is, and we knew it would be, the absolute max. But again, just keep in mind in general, if your situation has a restricted domain, then you should also check the quantity at the endpoints, in this case revenue or whatever you're trying to maximize or minimize, and make sure that it doesn't have a larger or smaller value at one of the endpoints than it does in between. Now, another thing is, I just wanted to mention, if you remember stuff that you learned in other coursework, since my revenue function is quadratic, and I know by the negative 3 in front of the p squared, it's opening downward, which we see in the picture when we use the second derivative test. The max is at the vertex, and I don't know if you remember, I just thought it would be a fun thing to remind you of. When we have the general form y equals ax squared plus bx plus c, the vertex is at x equal negative b over 2a. In this case, that would be negative 57 over 2 times negative 3, or as we found, 57 over 6, which again, we already knew that. We solved it using derivatives, but this is a situation where if we had our thinking caps on, we might have said, oh, it's a quadratic. Of course, the absolute maximum, it's opening downward, so it's got an absolute max, and that's where the vertex is. Be aware that in your textbook and on a quiz or a test, I would ask you to use the techniques of sections 4.2 and 4.3 to solve the problem. So you'll have to use derivatives to do these questions.